Welcome back to Insanely Huge Numbers. This is episode 2, and so a quick recap of the previous episode. In the last episode, we defined level operators, which is a family of functions with levels, which is this number 012. They look like L sub A of B and C. Alright. And then in the last episode, we discussed that L sub 0 of A and B is equal to A plus B, and L sub 1, which I will refer to as level 1 operator, is A times B, and then level 2 is A to the power of B. Alright, and then in this episode, this episode will be split into two parts, released separately, because while I'm doing this, it sort of hit my head that this is actually longer than I expected. Alright, so we will do two things in these two episodes. First of all, we'll talk about numbers in the form of a to the b, where b is more numbers in this form. So let's say 3 to the 7 to the a to the 9 to the 100 to the 1000. That's numbers in this form. These are exponential towers, and we will dive into their structure for a bit. And the next part we're gonna talk about, well, actually not next part, but like the end of the next part, we're gonna talk about L sub 3 of A and B. We briefly go over it last episode, but we're really gonna talk about it in the next one. Now, first of all, let's define what a base is. So, base 2, right? We're gonna start with what base 2 is, right? Uh, but base is essentially just this number a to the b, right? So in a to the b, a is the base, right? And then base 2 is a system with 2 as the base, which means it's a 2 to the something. And then the system that we use the most often is base 10, which have the 10 symbols 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Then there's also the system base 2, which only have 0 and 2, 0 and 1. Right, so basically means that the carryover rule only happens already when you have 1 1. So there's no 2 in the system. Yeah. And then these are basically the rules where you just add 1, and then if the digit is 1, right, then you just change it to a 1 0. If it's 0, then just change it to a 1. It's quite a nice base because addition is really easy, right? If you got two of the same thing, you just append it. You just basically add a zero to the end of the base, end of the number, and then say if both are zero, we just follow the same rule for base 10. Now this is better than base 10 because that there is only two cases, right? It's either 1 and 0 or 1 and 1, right? Because 0 and 0 just didn't do anything, right? But in base 10, there will be a lot more digits, right? We will have to include a lot more cases, like what do we do for 3 and 6? What do we do for 7 and 8, right? And then, but one downside of it is that base 2 is really lengthy, right? So, for example, the same number in base 10, let's say 1,000, it's gonna take 3.3 times longer strings to represent that number. So 1,000 is gonna be three zeros, and in base 2 is gonna be around 6 0. I mean, 9 zeros around, yeah, 9 digits. So an easy way we can make this a bit better, which is also how they actually did it in computer, is base 16, right? It consists of two units of 2 digits in base 2, right? And these are called bytes. And so it looks like 0 0 0 0 0 0, right? So this is a this this is a byte, this is a byte, and then 2 bytes make up a base 16 thing, right? Yeah, and then of course this doesn't really make it a whole lot better because you were still using base 2. But if we just map the numbers onto letters, like 1 to 1, 1 0 to 2, etc., and then we can just get 1 1 1 1 is F. So FF is 255 in base 10. Um, so we can actually represent all base with exponentiation, right? So for some base x, a n minus 1, a3, a2, a1, a0 are its digits. This is the same as x to the n, right, the nth number, times a of n times a sub n plus x to the n minus 1 times a of a sub n minus 1. Right, and you can continue this for the whole thing. Right, and will be the form that we're using. So base 3 or base 10, right? So throughout this series, we'll be using base 3 or base 10 for the following reasons. They don't use letters because for base 11 you have to use A, which is very strange, and we're not used to that. And then 3 is because it's often the smallest number for a function to really get big, right? Because 2 sometimes just doesn't work for various reasons, but a lot of functions just works for 3, or you just get huge suddenly. Alright, so we can break down numbers in base 10. In fact, we can do this for a lot of any other bases. We can, so basically 10 to the n becomes 10 to the n minus 1 times 10, and then we go 10 to the n minus 1 times 9 plus 10 to the n minus 1, and 10 to the 0 is 1. So we can just do all sort of these operations really easily. And then, so yeah, what if we have higher tower? Because this is only 2 heights, right? This is one number, two numbers. There's only 2 numbers in this tower. We'll call the layers of exponents heights. For example, 10 to the 10 to the 10 to the 10 has height 4, and so does 10 to the 2 to the 3 to the 4, right? But if we write it all in base 10, then this will be much. This will. I think it will only be height 3, right? And the 10 to the 10 have height 2, and the 10 have height 1, right? So we can check out some fairly simple structures using this heights description of numbers. 10 to the 10 to the 2, which is a height 3 number, is precisely a Google, because that's 10, right, to the 10 to the 2, and 10 to the 2 is 100, and to the 10 to the 100 is a Google. And I here define a number to be log k high x if and only if its highest power in the form of 10 to the 10 to the 10 to the k with height x and k less than 10. Right, so a Google is a level 2 height 3 number, right? And then we can see how we can translate it. So 3, 4, 6, 5, we break it down into this representation, right? Because we've talked about it here. We can use this rule to we can just reverse this rule and then get it to represent it in this way. And then we just look at the highest power, which is 10 to the 3, right? And then the height is only 2, right? And the level is 3, right? And exercise for the commenter: what is the level and height of 10 to the 10 to the 10 to the 10 to the 5? Now we can make definition for level and height stronger in the sense that it includes more numbers. It's more precise by using logarithms, so that we can assign a level and height for every real number. So we can have pi with respect to some base, and then we can represent it as levels and height, which is a pretty good idea actually, but that is not really needed for our purpose. So let's see. There are also more numbers that is level 2 height 3 using our definition, our looser definition, right? A Google is the least of those, right? They are L2H3, which is level 2 height 3, right? And there's a lot more numbers that is also L2 height 3 with our loose definition. So 10 to the 101, that's 1. 10 to 102, that's 10 times as much as this, and this is 10 times as much as a Google. That's 100 times, that's 1,000 times, that's I think that's 10 billion times larger. And then this is 10 billion, 10 billion. I think that's 100 billion times larger. And then this is a Google times larger, and this is a Google to the ninth times. I think that's gonna be 10 billion to the ninth times a billion. Yeah, yeah, which is pretty big. Believe me, this is a lot bigger than anything that we actually need. Well, actually, no. There for some probability, there is really low probability of some stuff to occur, and then the reciprocal of those probabilities is pretty high, actually. Now, these are decently massive, right? 10 to the 1,000 is at least L3 high 3. 10 to the 10,000 is the least level 4 high 3. And then 10 to the 10 to the 10 to the 2 is a Googleplex, which is the least level 2 and high 4. Now the amazing thing is that as the high go up, the levels actually matters a lot more, right? So at level at higher one, it might not matter as much, right? And then but at heights, let's say 10, it's gonna matter a lot more because it carries a repercussion of all the previous heights. So all the levels they all count. Now it's really difficult to get past L2 of H4, right? So we can have these gigantic numbers like 10 to the 10 to the 10 to the 2 plus 2, which is already 100 times bigger than a googolplex. Right? So googolplex is huge, and then you have to imagine 100 googolplex. And then this plus 9 is a billion times larger than the googolplex, and plus 18 is a billion times larger than the googolplex. And 27 is one more a billion, and then this is 100 plus 100 is a googolplex. Right, so you have to imagine Google many googolplexes, and 200 is googolplexes. Right, so you have to imagine Google many Google. I cannot speak. Google Google many googolplexes. Right. And this is Google to the 10 times larger than a googolplex, and then this is Google to the I think that's a billion. No, I think that's 1,000 million times larger than a googolplex. Yeah, so 10 to the 10. Wait, actually, this is level 2.01 of high 4. Is a googolplex, googolplexes. Yeah, so it's really insane, right? And then the most insane part is that this number actually grows larger as the level go up. So like at level 3, we can get the thousandth, and then it's gonna be the same thing, which is you know times multiplying by 10 of this number, and then it's like multiplying by 10 by itself for 10 times. Yeah, and then level 4 of high 4 is a lot bigger, a lot bigger. So how much bigger? It's not even comprehensible, right? And we'll get to this in the next part, but yeah, we're just gonna finish this off one here, and I hope you enjoy this one. If you like this one, please consider commenting, subscribing, clicking the like button, and turn on the bell. Thank you. Thanks for watching. I hope you enjoyed this one.